Alright guys, welcome back to another lesson. Today we're going to be talking about acid and base titrations. So this is a subject that usually comes up. Acids and bases tend to come up in the ionic equations chapter, and there's varying degrees of what you have to know, but one of the things you have to know is how to do a basic, simple titration with an acid and a base. So to start us off, I wanted to recap briefly, and you can go to a different lecture that is talking about acids and bases, but this is just going to be a recap. Acids, we're going to define at the moment anything that gives off an H plus in aqueous solution. This is technically the Arrhenius definition of what an acid is. And then a base is going to be anything that gives off a minus OH in aqueous solution. And again, that's the Arrhenius definition of a base. So there are other definitions, like the Bronsted-Lowry definition and the Lewis definition of acids and bases. Now those are a lot more broad, so we're going to stay away from them for the time being, and we'll come back to them in a later chapter. But for right now, an acid is anything that gives off an H plus in aqueous solution, and a base would be anything that gives off a minus OH in aqueous solution. And we also went through in class, and you can go back and check some of the other lectures, a list of strong acids and bases. A strong acid will completely dissociate 100% in solution to give 100% hydronium ions. Alright, so let's talk about a strong acid and a strong base if we mix them together in a reaction. So when we have a strong acid and a strong base, and I've selected one of each from our list of 6, that come together, they're going to form a salt and they're going to form water. So you can see an example of that down here. So as we look, H2SO4 is considered a strong acid, NaOH is considered a strong base. They produce sodium sulfate, the salt, and water. Now this is a balanced reaction. If you were ever given the reaction and it wasn't balanced, you would need to be able to balance it. And if you have any issues with that, then you need to go back and you need to revisit the balancing video. Now, we can react an acid and a base together via titration. So that's the method we usually use when we're reacting an acid and a base together. A titration uses something called a burette. It's a very, very long, skinny, narrow piece of glassware that's got a stopcock on the end so that you can allow a flow of your desire. You can have it just drip a little bit, or you can have a very steady stream. Now we tend to try to be very careful with titrations so we don't overshoot what's called the equivalence point or the end point. So when an acid and a base are at the equivalence point, which means there are equal amounts of H plus and OH minus in solution, we're going to use an indicator to inform us that the reaction is complete. So phenolphthalein is one of the common ones that we usually talk about in class. There's a whole variety of indicators, but a good indicator should change color based on pH. And you're specifically going to look for an indicator that's going to change in the pH range that you're looking for the neutralization to occur. So for a strong acid and a strong base, that's usually around a pH of 7. And you can see the picture over here has a drop of phenolphthalein in the solution. It tends to give a pink color. Now, if it was at the end point, that pink color would spread throughout the solution and persist. If it wasn't at the end point, you would shake that up and the pink color would go away. It would become clear until you hit your end point or your equivalence point. So let's actually go through a titration. So titrations are good for figuring out unknown concentrations of an acid or of a base. You're going to need to know a little bit more information about one of them, and then the other one can be the unknown that you're titrating your liquid into. So let's take this example. You titrate 57.8 milliliters of a 2.50 molarity sodium hydroxide solution to reach an endpoint for 70 milliliters of a sulfuric acid at some unknown concentration. All right? Find the molarity of the acid. So what this is saying is you, as the chemist, made up a 2.50 molarity solution of sodium hydroxide. You filled up your burette, and it required 57.8 milliliters of the sodium hydroxide in order for the indicator to show up in 70 milliliters of a sulfuric acid solution. And we don't know the concentration of acid in that solution, we just know the volume. So what we're going to do is attempt to find the molarity of the acid. So of the acid. That's what the question is asking us. So what's the first thing we should start with? Like most equations or problems that we do, you're going to look for the balanced equation. And it's given to you here. Again, you should be able to balance this if it wasn't balanced. But you can see that we have a balancing of 1 mole of sulfuric acid for every 2 moles of sodium hydroxide when we're completing this reaction. And that's going to be important in order to find out our moles of acid, which will eventually lead to our molarity or concentration of acid. So, the next step is to find the moles of the known acid or base, and we're going to find this through using molarity. So if we come back here, our known in this case is the NaOH, and we have the information we need, the volume and the molarity. We're going to use those pieces of information to find the moles of sodium hydroxide that were used. Now, if you are unsure of how to calculate moles when you're given molarity and volume, you should go visit the molarity video, and that will teach you how to do that. So, if we get ready to work this out, we're going to say, okay, the molarity of the sodium hydroxide is 2.50. We're going to set that equal to X moles, and that's moles of sodium hydroxide that we're working with. And then if you go back and you look at the volume is 57.8 milliliters. We need that in liters. So in liters, it's going to be 0.0578. And if you're having issues with conversions, go back and watch the conversion video. So you should be realizing all of these concepts, they start piling on top of themselves. So you can't skip learning, your unit conversions. You can't skip learning molarity and continue down the road, because these all go back and start building on themselves. You need to know molarity. You need to know how to balance equations. You need to know unit conversions. Alright, so if I want to find X, I need to multiply each side by the 0.0578 so that it'll cancel at the bottom here. I'll multiply it times the 2.50, and then that will give me just the moles. So if I end up doing that, and I multiply 2.50 times 0.0578, which is my volume in liters, we'll put the liters down there, what I end up getting is that X, which is the moles, is equal to 0.145. Alright, so take a second, put that in the calculator. Take 2.50, as you're practicing with me, times 0.0578. So algebraically what we did was we times the left side by that, and that's what we have down here, and then we times the right side by it, and it cancels out on the bottom to just give us X. So 2.50 times 0.0578 gives us X, and X is 0.145 moles of sodium hydroxide. So that's the total moles of sodium hydroxide we use. So we're off to a good start. What's the next thing we need? We need to find the mole-to-mole ratio of our known acid or base to the unknown acid or base, and then find the moles of the unknown from that. So in this case, the acid is the unknown. The base, which we just worked with, is our known. So we know we're going to start with 0.145 moles of sodium hydroxide. So let's put that down. 0.145 moles of NaOH. And then what we're going to do, we're going to set up a conversion. And we want to get into moles of the unknown, which is H2SO4. We don't know how many moles of H2SO4 there were. We only know the volume. It said that there was 70 milliliters worth of H2SO4. Now, we're going to also put moles of sodium hydroxide on the bottom here. Now, this is like your limiting reactants. You need to go through, and the only way you can convert from one mole of substance to another mole of substance is through your balanced equation. So if we go back, one too far. If we go back and we look, the balanced equation tells us that there's an implied 1 here, and then I have a 2 for my sodium hydroxide. So it says for every 2 moles of sodium hydroxide, I can neutralize 1 mole of H2SO4. That's what the balanced equation is telling me there. So if I go back over here, I say every 2 moles of sodium hydroxide can neutralize 1 mole of H2SO4. So let's find out how many moles of H2SO4 we neutralized. The 1 will drop out here, so what we're really doing is taking 0.145 and dividing it by 2. So take a second to do that in your calculator. And hopefully the number that you get should be 0.0723. This is the answer right here. All right, that's the moles of what? H2SO4. All right. So once we've gone through this value right here, the 0.0723 moles of H2SO4, that's the moles of H2SO4 that we need in order to find the molarity. So if we go back to the original problem, what did it say? Find the molarity of the acid. So we're almost there. Use the volume and the moles of the unknown to find the molarity. So remember, molarity is equal to moles over liters in volume. So I have my moles, right? So I can say my molarity is equal to M. We'll find what M is in a minute. My moles are 0.0723. And my volume, if I go back and check on my volume, I had 70.0 milliliters of sulfuric acid. So I can come in and put that in here and say I've got 0.0700. That is in liters at that point because molarity has to be in liters by its definition. The unit is moles per liter. And take a second to calculate that. Put that into your calculator. So you should notice the numbers are pretty close to one another. 0.0723 and 0.0700 are almost identical, and a number divided by itself is 1. And indeed, if we solve it, we find 1.03 is the molarity of the H2SO4. Alright? And so that's how you would do an acid-base titration. You would need to know the concentration of an acid or a base that you put in the burette. You can have some unknown concentration, and you're going to do the titration to a certain endpoint. You will need an indicator to recognize when that endpoint hits. And then once you're at your endpoint or your equivalence point, you're going to go ahead and you're going to run your calculations through using mole-to-mole ratios to find the concentration of the unknown. So thanks a lot for watching, guys. Hopefully these videos are continuing to help you as you prepare for tests. They can serve as good reminders that you go back through as you're learning. So please remember to comment if you have any comments. Like the video if it was helpful, just so that I know. And then, again, I strongly encourage you to subscribe to the videos because that is going to be the quickest way for you to realize that new material is up. And there's going to be a lot of it coming out, especially before test weeks. So thanks a lot, and I'll see you guys next lecture.